Silicon carbide made EVs faster and cooler. But what if the next jump in chips could double range and cut charger time in half? In this video, we'll peel back the curtain on the semiconductor race that's quietly shaping electric cars. You'll learn why silicon carbide mattered, what its limits are, and which new materials and design could actually move the needle for the battery life, charging speed, and cost. Stay with me, by the end you will know whether the next chip revolution is hype or the real game changer for EVs on the road tomorrow. Think of the power electronics in an EV as the car's traffic controller. They convert the battery's DC power into AC that drives the motor, steer energy during regenerative braking, and manage charging. For years, those controllers used silicon transistors. Then silicon carbide arrived, and suddenly we had the chips that run hotter, switch faster, and waste less energy. That meant smaller cooling systems, lighter inverters, better efficiency, and faster charging. Silicon carbide was a step change, but every step change has a ceiling. Silicon carbide is great at high voltage and temperature, and it wins in efficiency. Yet it's expensive and hard to make at scale. It also runs into physical limits when engineers try to push switching speeds higher or shrink device size further. Manufacturing yields and material defects make scaling tricky, and the supply chain for the wafer and processing is not trivial. That's where the hunt for the what comes after silicon carbide really begins. There are multiple contenders. Gallium nitride is one that's already seen a lot of hype. It can switch even faster than silicon carbide and can be made on smaller, cheaper wafers in some cases. Then there is a lineup of newer materials and architectures: diamond-based devices, ternary compound semiconductors, heterogeneous integration methods where different chips are stacked and connected at the substrate levels, and advanced packaging that brings control logic, sensors, and power stages into the same physical block. Each approach promises different wins: lower losses, higher switching frequencies, smaller passive components, and ultimately cheaper and lighter powertrains. Why does switching frequency matter? Higher switching frequency means the same power can flow through the smaller inductors and capacitors. Those passive parts often take up massive volume and weight in an inverter. Shrink those and you suddenly free up space for battery or cut vehicle weight, which itself improves range. Faster switching can also tighten control loops and improve regenerative braking fidelity, which makes the car feel sharper and captures more energy back into the pack. But new materials bring new headaches, meaning manufacturing at scale requires new tools, new fabs, new supply chains. Thermal management changes when switching speeds increase, because heat distribution becomes different. Electromagnetic interference is a bigger problem when switching is faster and edges are steeper. And of course, safety and reliability validations that took decades for silicon need to be rerun for anything new. Car makers value proven technology. They move cautiously because a failed power stage can stand the driver on the highway. So here's the core challenge. How do we get the benefits of the next generation semiconductors without exploding costs, reliability, risk, or manufacturing headaches? Automotive companies want lower losses, better thermal performance, and cheaper systems per kilowatt. But they also need chips that also last 10 to 15 years and survive every pothole, temperature spike, and software update. If a new material delivers 20% more efficiency but halves yield or doubles validation time, it's a tough sell. There's also the infrastructure angle. The power electronics inside the car matters, but how they interact with chargers and the grid matters too. Faster switching and higher efficiency could allow smaller, cheaper onboard chargers and less stress on the grid side equipment. But the grid itself must evolve to handle tens of millions of cars pulling fast power. So the semiconductor revolution is necessary but not sufficient. It's a piece of a bigger puzzle. Let's walk through promising paths one by one. Gallium nitride, or GaN, is already a reality in some high-frequency power supplies and data center gears. For EVs, Gallium nitride offers lower conduction loss and far faster switching. That means you can shrink the inverter and push higher charge rates without massive heat sinks. Companies working on gallium nitride for automotive aim to solve reliability at high voltage and build automotive grade packages that can handle vibration and moisture. The big benefit is gallium nitride can use smaller passive parts, and those smaller parts cut cost and weight. Beyond gallium nitride, there are research level contenders like diamond based semiconductors. Diamond has insane thermal conductivity and can operate at very high fields. Lab test diamond devices can switch incredibly fast and tolerate very high temperatures without degrading. The catch is manufacturing. Making single crystal diamond wafers at size and cost that matters for auto production is still a science project. But if that barrier falls, the thermal benefits could be revolutionary. Another approach is heterogeneous integration and advanced packaging. Instead of relying on a single better semiconductor, engineers blind the right material. Another approach is heterogeneous integration and advanced packaging. Instead of relying on a single better semiconductor, engineers bind the right materials together in a package that combines the strengths. For example, use silicon for control logic, gallium nitride for SiC for power switches, and embed high efficiency passive components directly in the package. This co-design reduces the distance between components, cuts parasitic inductance and capacitance, and lets engineers optimize the whole power stage rather than each piece alone. There's also the system level benefits of moving from discrete bulky inverters to more integrated motor drive modules. When semiconductors shrink the size of the power electronics, designers can place them closer to the motor or even integrate them into the motor housing. That reduces wiring losses and allows for better electromagnetic compatibility. It also makes thermal paths shorter and more controllable, which feeds back into efficiency. Then there are manufacturing tricks. Some firms propose making gallium nitride on silicon substrates or to reuse the massive silicon fabrication ecosystem. Others explore chiplet approaches, where many small tested silicon components are tiled into a power stage, improving yield and reducing cost. Those are clever ways to leverage existing tools while still getting new materials benefits. But for each technical win, we must validate lifetime. Cars stay on the road for a decade or more. A new semiconductor must survive thermal cycles, humidity, vibration, voltage spikes, and software stress. That's why the translation will be gradual. You'll see gallium nitride in auxiliary converters and chargers, then in main traction inverters for performance models, and then scaled to mass market as cost, reliability, and supply mature. Here's the big moment to understand. The next big semiconductor revolution for EVs won't be a single material winning overnight. It will be an ecosystem shift. Imagine an EV where the inverter is 40% smaller, the cooling hardware is 30% lighter, and charging losses drop so much that 80% fast charge takes half the time and half the energy waste. That scenario is possible, but only if material improvements, packaging, supply chain changes, and the system level design all land together. The winning path will be the one that balances performance gains with manufacturability and lifetime reliability. If that alignment happens, effect ripple across the whole EV value chain. Cars get cheaper to build and operate. Batteries can be slightly smaller or give more range. Charging stations require less power and handle more cars. Grid integration becomes easier because each car is more efficient. That's not small. It's a structural change that affects cost, consumer acceptance, and even design language of cars. To wrap this up, silicon carbide was the key step that unlocked modern EV performance gains. The next step is not a single silver bullet, but a combination of new materials, smarter packaging, and system-level designs. Gallium nitride is the near-term candidate with real promise. Exotic materials like diamond shine in the lab, but need breakthroughs in the fabrication. Advanced packaging and heterogeneous integration may give the best trade offs between performance and manufacturability. The real winner will be the approach that delivers tangible efficiency gains while being reliable, scalable, and cost effective. This change won't be overnight, but it will be transformative. Over the next decade, expect incremental rollouts like gallium nitride in chargers and power supplies, hybrid gallium nitride silicon in high performance cars, and the broader adoption once yields and costs improve. When that happens, the whole EV stack gets lighter, cheaper, and more efficient. And the user experience, faster charging, better range, and lower cost becomes the proof.